Recording is rolling. It is Monday, August 18th. Welcome back from the weekend. So, what have you guys today? You guys have this table. What you guys do is we're going to be doing some trigonometry. We'll be we're looking at right triangles and the properties of right triangles. And I'll show you guys why. Because, guys, the activity that we do today, we're going to apply these skills throughout the class all year. It's never going to go away. It's going to involve vector components. Okay. Now, on the back side of this page is a model right triangle. You guys see the sides are marked X, Y, Z. Okay? And also, guys, look at these angles right here. You guys see the angles in the corners are marked. What are those letters right there? Alpha and beta. You're starting to get some Greek. Right. Now, you guys do see this is a right triangle, right? Because it's got that little square corner right there. Right triangle, 90-degree angle. Okay. The idea here is that if you know a little bit about a triangle, if you know enough, in principle, you can solve everything else. So there's 10 different setups here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see that? Okay. So I'll give you some information about the triangle, and there is in principle enough to figure out everything else. Okay. Some of these the angles are going to be in degrees. But you guys see the sides? I also gave you guys some units, like meters, like, how far over, how far up in meters. There's also meters per second. So you can also apply this geometry to like velocities or newtons, measures of force, Newton seconds. So it's like a momentum type unit. Okay. So anything that's a vector quantity, you can say like how much over, how much up. Okay. You guys see the principle? Okay. So we're going to get as far as we can on this today. My plan is to pick this up from you guys by Thursday. So Thursday, 8/21. You guys can write that in your planner. So we'll have a few days to do this. On Thursday, I want to actually kickstart the first main topic by AP's book, which is kinematic motion, linear motion. So I'll have some incline set up in the lab table. Give you guys some Hot Wheels cars. You guys roll the Hot Wheels cars down. You're gonna measure how far did the Hot Wheels car roll, how much time, how stopwatches. Use your protractors to measure what's the angle. That'll be important later, a few weeks from now. And also, I'll give you guys little speed gates. You can say how fast the car going through. So we're going to crunch a bunch of data, and that'll kickstart linear motion by the end of this week. AP. So for my AP classes, you guys in front of me are AP. Over the weekend, I did open up some AP assignments. Now, some of them aren't really assignments, but I had some requests from some students just to open up some old questions so you can just play around with it. Right? Now, one that eventually will make do. I think I put a date on it. It's probably going to change for Unit 1. So there's no like real due date yet. But if you want to like poke around or read some of the questions, you could. Okay. Right. Over this weekend, I was planning the next few weeks. So I want to kind of get the next quiz on the board if I can. I'm looking at Thursday, August 28th. So that's not this week Thursday, but next week Thursday. That's the earliest I would get you your next quiz. So I'll see if I can get it by then. And here's my plan. I want to try something different this year that I haven't really done in the past to see how this works. Is that every day after school, I'm going to go home and review what I did with the guys in class and write down on one or two or three questions that I thought were interesting from the class that day. And then slowly compile a quiz. So I haven't written anything for the quiz yet because I'm going to be starting today. And then on whenever the quiz day is actually going to be, which might be Thursday, August 28th, I will give you guys the quiz, and it'll be the stuff that we did in class. So if you're following along, solving stuff, taking good notes, then you should be good to go. Okay. Any questions so far about any of this agenda stuff? Okay. Textbook. I'll do this for both AP and also for my honors class. This is what we're doing. Similar activities today. So I have AP, I have honors. Start with AP. So AP, this is your guys' book. It says college physics. Now, this is a brand new book. All science classes got brand new books. Okay? And I've been going through this. This looks pretty good, like pretty solid. It's actually designed exactly for this class. Like here it is, AP Physics 1, you guys. Right? The difficulty with this book is it is so big and heavy. I'm imagining, do I want to have you guys be like lugging this through school every day? I don't know if that's really reasonable. It's just so big and heavy. So here's what I think I want to do with books is to have a set in class and we'll probably be reading out of these a lot in class, have you guys solve a bunch of puzzles at the end of the chapter kind of thing. Right? And I did over the weekend scan the first 3 chapters. I don't know, did you guys see I posted that to Google Classroom over the weekend? Okay. So if you want a digital version, you get I got the first 3 chapters scanned anyway. And then as we go throughout the semester, I'll scan more and more. If you do want a physical copy to have in your hands and take home, then let me know. There might be like 2 or 3 or 4 students that want something like that. Just let me know sometime, and then I will check out a copy to you. Because other than that, you'll have a class copy. All right. Now, here, I'll say this for honors, just to have this also for the recording. Now, the honors books haven't quite come in yet. I do have the teacher's version, but this is like the only one I have. So I don't actually have the books. Oh, also for both AP and honors, I was hoping they would show up on your Launchpad, but I haven't seen any of them. Have you guys seen anything like that? Any digital version? I haven't. I think it's supposed to be. Now, the honors, I just saw this for the first time, like in the last 3 days. And I don't know what I'm going to do about this, but there are no actual questions in this book. I don't actually have any questions at the end of this chapter. I don't know if they're supposed to be online or something. I do have materials from the past I'd be able to use if I can't use the book. So I don't know. I'll figure something out about that. Right. This detail right here, there is FAST testing coming up next week. It looks like mostly on Tuesday the 26th, although some students not on Tuesday the 26th. Okay. This mostly applies to 9th and 10th graders. So if you're 9th and 10th grade especially, then I did modify an Excel page and posted that to Google Classroom. So see if you're fast testing and where you're supposed to reroute. Right? Oh, even if you aren't testing, some of your classes might be relocated anyway, so maybe kind of be aware of that. Okay. All right, that's a bunch of announcement stuff. So you guys good with all those announcements? Good. Okay. Right. So of course we're going to be measuring a bunch of angles and sides on a bunch of triangles today. You guys have calculator within reach. Okay. Before I quite get to this table, I want to show you guys some of the application of the skills that you guys are going to be getting today. Okay, so I have a stack of posters throughout the school year. So I'll start with this one, Pythagorean theorem. Now, guys, Pythagorean theorem, if you apply the Pythagorean theorem, what kind of triangle do you have to have for this to even apply in the first place?
Right triangle.
Right triangle. Yes, this blue right triangle right here. You know it's right triangle, the 90-degree angle. Right? I can measure that out. Like, oh yeah, that angle right there. Bam, 90 degrees. 90-degree angle. Well, we'll square it. Okay. Now, if that's true, then you have to say this side squared plus this side squared is equal to this side squared. Yeah. Another way to say it is this pink square plus this green square. Does that add up to the area of this yellow square? That's the same thing, isn't it? Right? How about guys, what if it is not a right triangle? Did you guys learn in math class something called the law of cosines? Does that sound familiar? Law of cosines, right? That's more like a generalized version of this. So it's a little fancier. I don't have that version, but even if you have a triangle, it's not a right triangle. Here, I'll draw something up just to really hammer this point. Like, what if I have a triangle that's definitely not a right triangle? Right? How could I make sense of this? Could I, if I wanted to, split this into little triangles that actually are right triangles? Yeah, good little tricks, right? So if you know right triangles, you can kind of do it if you want, right? And the area of a triangle in general, could that be base times height divided by 2? Right? And if you do have a right triangle, then very conveniently, based on the height, could just be the 2 legs. Just do that leg times that leg, and then that would make a big rectangle, and then slash that in half or divide by 2. Yeah, okay. Right. And if it's not a right triangle, then this line I drew in the middle, could this be called the altitude? And then this could be your base, call it B for base. This could be your height, I'll call it H for height. Right? And then could I still apply base height divided by 2 for this looking triangle? Yeah, that'd be fine. Okay. It's just that the height would not be one of the legs in that case. Okay. All right, so you guys good with that? Okay. All right, now this one right here, this is the star of today, this poster is. And if you see this hanging in class. So start off with the definition of sine, cosine, and tangent, like straight out of the textbook. So now this is a right triangle. So we have a right triangle. Okay. And if I'm just focused on the triangle aspect of this, then there's, of course, one right angle, and there are 2 acute angles. And I have to pick one of those acute angles and hone in on that. So you know what? I thinking about some. Okay, all right. There we go. Get this out of the way. Okay. So notice I picked this angle down here and not this one up here, because that might reverse some of these definitions. Okay. Guys, what character is this right here? What's that called?
Theta.
Theta. Right. So now we're getting some more Greek. You guys might see I have a couple of Greek posters in this class. If you're sitting in class, you guys see those 2 over there on the wall? Right. That's these 2 right here. Now, this is not the entire Greek alphabet, but this is, I think, everything you're going to really need for this class. And we'll use most of these Greek characters, right? So right at the top, alpha and beta, those are used for angles. And later on in class, alpha we'll use also for angular acceleration, but we're not ready for that yet. Here's theta, which is also used to measure angles, right? Or how far something turned, called angular displacement, which is basically an angle anyway, right? Yeah, so be familiar with these Greek letters as we go on through class because you guys are going to see all of those. Okay, so got some Greek. Okay. So sine of an angle is defined as the opposite leg compared to the hypotenuse. You take that ratio. You see that there? Right? So for example, this angle right here, if I measure it with a protractor, so I'm going to take the node of the protractor, park it right on that corner, zero out this leg. See what this leg swipe through? Right. And this is a little over 30 degrees. I'm going to round it just for this next example. Okay, suppose this angle was exactly 30 degrees. Right? Does anybody know? Maybe somebody knows. What is sine of 30 degrees? Does anybody know that? Guys, over a unit circle? Sine of 30 degrees. It's one of your special angles.
Is it 0.5?
0.5, exactly. 0.5, right? Guys, try this. In your calculator, hit sine. Guys, a little sine key. Hit 30 for 30 degrees. Okay? Your calculator should say 0.5 or 1/2. Okay? Because if it does not, then it's possible that your calculator is in radians, which is a different way to measure angles that we're not going to worry for a few weeks. Today, we're just using degrees. You guys see this little key at the top says DRG? If you click that, then you can switch it, but I want to keep degrees, okay? So everybody's calculator today is in degrees, okay? Everybody's in degrees, right? It's important that you communicate with the calculator the unit for your angle so it knows what to do, okay? And what that means is this. If this is a 30-degree angle, which actually is pretty close to, can I measure this side B, which looks like so many centimeters, it looks about 7 centimeters long? Can I swipe that over and go 1, 2, and be exactly 2 lengths of B to match this C right here? That works for a 30-degree angle here. This is about 14 centimeters. Yeah, sure, it's about 14 centimeters. Look at that. 7 compared to 14 is a 1 to 2. For 30. Cosine of this angle is the adjacent leg compared to the hypotenuse. So adjacent over hypotenuse, right? And then tangent is the ratio of the 2 legs, so B over A in this case. Okay, so you guys got the definition of sine, cosine, tangent? Right. Now, if you know that, then really how you apply those in this class, like 90% of the time or more, is actually this rearranged form of these 3 down here. You see these 3 little tiny boxes, right? Can I just take the C hypotenuse and very simply cross multiply that and do C times sine theta equals B? And that says this green box right here, right? And then C cosine theta is A. Oh, okay. Okay, is that right? Actually, this last one I'm going to cover up. I'll come back to that later. Okay. Right. So, see, the title of this poster is called Vector Components. So if I'm, say if you're moving northeast, you know, say like, how much north? How much east? Do you guys see that these 2 boxes could exactly answer those questions? Right? What if I'm pushing something up and to the right? I got this little kitty cat stamp right here. What if I'm pushing this up to the right with some force I can measure in newtons? I want to know, how much am I pushing up? How much am I pushing to the right? Because you'd want to quantify those. You guys see that? Right? You guys see that those you can exactly answer with these 2 questions right here? So these 2 boxes know by heart. Because most of the time in physics, you know the C, you know the hypotenuse. Like, oh, I know I'm pushing with a total magnitude of like 10 newtons or something, right? And I know what this angle is. So now I can just do C sine theta and C cosine theta to figure out how much up and how much right. You guys that? Right? I wouldn't be surprised if you apply these calculations 1,000 times in this class before you graduate this class, right? It's very good. Now, the one I'm covering up down here is actually how you can extract an angle. It's one way to extract an angle. Notice so far, I'm assuming that you know what the angle is. Like, if I know it's 30 degrees, I can just plug in sine of 30 degrees right here. But what if you only know the 3 sides? For example, you guys ever heard of a 3, 4, 5 right triangle? Right? Are all right triangles 3, 4, 5? No, right? But a 3, 4, 5 triangle is a right triangle, right? Interestingly, right? So what if B is 3, A is 4, and C is 5? That could be possible, right? Does anybody know what angle applies to a 3, 4, 5 right triangle down here? This little tiny angle? More than 30. Less than 60. Huh? Less than 45. Right? How about this? Huh? More than 35. Okay. Less than 40. How about this? Less than 38. Does anybody know a method? Does anybody know a procedure you could use that maybe covering up right here? A procedure you could use. Does anybody know? Inverse trig, right? So inverse tan is what I went with here, right? So here's what I want you guys to see, big picture, is that you're allowed to take a sine or a cosine or a tangent for that matter of an angle it will spit you out a ratio. For example, that's what we just did a few minutes ago. Sine of 30 degrees, and the ratio is 1/2, call that 0.5. Okay. The inverse of that is you can take an inverse trig of a ratio, it'll spit you out the angle. That's what we're about to do right now. You guys ready to do that? Right? So now if I'm playing off tangent or inverse tan, I'm playing off the two legs, right? Not the hypotenuse, but the two legs. And if we're doing a 3, 4, 5 right triangle, guys, try this. Hit second and then hit tan. It doesn't say tan then -1, so inverse tan. So does anybody have trouble accessing inverse tan? You just hit second tan, get inverse tan, right? So it's called inverse tan. On Microsoft Excel, they also call it arctan. If you write a tan on Microsoft Excel, it'll do an inverse tan, right? Arctan, right? Right. Now, if I want opposite over adjacent to refer to this angle, would that be 3/4? Right, guys, try that. 3/4. Yeah, you see 36.8 something degrees, right? Oftentimes you'll see that rounded to 37 degrees. Okay, guys, if you're ever getting an AP free response question for my AP class, right? And you see a 37-degree angle, you guys think they're setting up some 3, 4, 5 geometry? Yeah, you'll see that quite a bit. Okay, right, right. So look at that. Okay. And here's some applications of these. So in a few weeks, we'll do some projectiles. Ooh, could this be a projectile? Where's this ball going to land downfield? Well, if you know the blast speed, suppose this cannon's blasting like 100 meters per second, and you know this angle, you can right away get how fast across the field it's going. Take 100 meters per second times cosine of, how many degrees? And how fast it's going strictly up. Take your 100 meters per second times sine of whatever this angle is. Now the vertical one's a little trickier because gravity immediately starts pulling it down. But you can get an initial value. Okay, guess that. Right? So we'll be doing this in a few weeks. Right? Here's a more expanded version of the same idea. Got two that go together. You guys see, pow. Oh! What triangle did I just set up right here? A 3, 4, 5. And what angle is that? 37. But you guys know it's really like 36.86, whatever, right? Okay. I'll call it 36. Hey, look at that. And then that's the first step to kickstart this whole process. You figure out how far does the cannonball go. Guys see that? Yeah. How about this? I'm calling this a joint in tension. Maybe like a bridge joint, or what if I have a lab weight? That's what this apple represents, like a lab weight. And I have a couple of spring scales. And I want to know, like, what's the force on the right side? And what's the force on the left side? The right spring scale and the left spring scale. You guys think if I know this weight, and I know these angles, alpha and beta, I could figure out what these tensions are? Yeah, in principle, right? Now, here's the guiding principle, is that the sum of the forces in the horizontal goes to 0. Do you guys think these two blue components, this one pulls right as much as this one pulls left? They zero out. And you guys think the vertical components, do you guys think this one pulls up, plus this one also pulls up a little bit? Zeroes out with this big weight pulling straight down? That's the screen condition. But to solve that exactly, you need some sine and some cosine. Right? You guys see that? Yeah. Hey, how about, did I show you guys a fun bus going around a bank curve the other day? Right, how much you have to bank the road? Now, there's a full process that I don't have the whole process written on this page, right? But you guys see it's going to involve some sine cosine, which they make a tangent right there. Let me pause this and grab this phone call. Yeah. All right, and we're back. All right, so someday we'll be doing like going around curves. Ooh, I like this one. This green banner means energy, conservation of energy. There's a framework to solve this. Okay, suppose you have a pendulum set up. Maybe I put this on a string. Let it go. Swing, swing, swing. Right? The opening scene of Indiana Jones swinging on a vine. How fast is it going down here at the bottom? How fast? How can you figure that out? Do you think that has something maybe to do with this height change? You guys see a little height change right here? But how could you get that? Does it have something to do with this geometry, this triangle right here? Do you guys see a nice right triangle hidden right there? Right? But there's going to be, I see a cosine. Sine, cosine. Okay. You bounce a ball off a wall. You guys see this ball, boing, bouncing off a wall? It comes at some angle. I wonder what's the force from the wall? Boing, you think there's some force from the wall to make it sort of reverse direction, at least along the x-axis, right? So I see a little sign right here, a little sign. Depends what angle you throw it at. If it's head on, it's more of a force. If it's got shallows, boing, probably not much of a force. Right. Okay, and this is what we're getting to today. Right. So you guys get so far some examples. Right, so yeah, guys, all these trig components, sine and cosine. Yeah, this is never going to go away. It's so know all this stuff. Where's my page here? Back in. All right, so here's what we do. Everybody has a protractor. Here's a protractor. Okay, so write your name on your paper. Write your name. Okay, now here, I'll put period 4, first 4 period, I think, right? And then the title is going to be Trigonometry Lab. Trigonometry Lab. Yeah, Trigonometry Lab, good name, right. I started setting up a table for you guys, but right. Well, okay. So everybody got that. Now, do you guys see this baseline right here, cutting straight through the middle of the paper? And there's 3 dots. You guys see these 3 dots right here? 3 dots. We're going to set up 3 right triangles. You guys ready to make 3 right triangles? Okay. So start with those dots. Take your protractor. Put the node of the protractor right on top of the first dot. Zero out that baseline. Dot, baseline, zeroed out. Okay. Go up to 90 degrees. Make a little mark at 90 degrees. Okay. Then straighten that out. Straight edge function. Zip. Okay. You just made a right angle because you just measured off 90 degrees, didn't you? Okay. Got a right angle? Let's do that for the other 2 dots. So take the node of the protractor, park it on the second dot. Zero out that baseline. Go to 90 degrees. Make a mark right there. Okay. Then straight edge. Zip. Up. There's the second right angle right there. Okay. And the last one. Node of the protractor on the dot. Zero out that line.
Doesn't matter how big or
90 degrees. Okay, well, not really, but guys, the bigger you make your triangles, the easier it's going to be to use the protractor. Because if you make a little tiny triangle, like, yeah, I'm going to break out my magnifying glass, then you think it's kind of hard to measure with the protractor. The larger your triangles is, the easier it is to measure with them. Okay. Okay. So I have 3 right angles here. Now I'm going to draw 3 random right triangles. So here it is. First one I'll make kind of flat, shallow. Maybe this next one's kind of even-ish. Right, and this third one I'll make kind of tall and skinny. Right, about like that. Okay, so I got 3 right triangles. Yeah, you just don't have to look exactly like mine. Just 3 different triangles. Okay, you guys got 3 different triangles also. 3 different triangles. 3 different triangles. All right, guys got those. Got those. All right. All right, I'm gonna label these triangles. So I'll call them, how about triangle A, triangle B, and triangle C. Okay. Then on the table, see the very first column says triangle, and then, well, units, I'll come back to that. And there's 3 rows beneath those. So I'll label that triangle A, triangle B, and triangle C. Now you can name your triangles whatever you want to. In the past, I've called them like Schrodinger, Heisenberg, and Kepler or something. I'll just call them A, B, and C. Okay. Okay. All right. You guys up to where I am? You guys good?
Yes.
Okay. Okay. All right. Oh, now I need to label some sides and some angles on these triangles. So let's do. Right, let's do this. The bottom left corner, call that alpha. And then this top right corner, I'm going to call beta. Okay. And then next triangle, I'll do a similar thing here. I'll call this guy alpha and this guy beta. Of course, they'd be a completely different triangle, so they don't really match, but okay. Okay. And I'll call this alpha, I'll call this beta. Just so I have some angles that I can point at and measure and write on a table. All right. All right, so everybody got their alpha and their betas. So alpha down here, then beta is the top right corner. I need to label the 3 sides. So the bottom side I'm going to call X, and the vertical side I'll call Y, and I'll do that for all 3. Right? So I'll call this X, call this Y, I'll call this side X, and I'll call this side Y. Right? So I have X and Y for all 3 of these. Right? And a hypotenuse I'm going to call Z. So Z, Z, Z. Right? So now I got some labels. Right? So I named all my triangles. The angles I called alpha and beta, or well, the acute angles, I should say, called alpha and beta. Okay? And then the 3 sides are called X, Y, and Z, where Z is the hypotenuse for each one. Okay? All right. How do you guys do then? You guys up to where I am? Is good? Yeah. Good. All right. Now, how about this table? All right, so I got triangle. Okay, A, B, and C. Right. Now, what are we gonna measure here? So going across, have you guys measure side Z? Wait, do I want to do that first? Yeah, why not? Let's do it. Okay. So side Z. Okay. Okay. Then go alpha and beta. Okay. Oh, I should be including units for all these. Because this is a really important part of this class too, is that any number in this class should have units attached to it. Well, except for a couple of unitless exceptions. Okay. Guys, what do you think we're going to be using to measure how long is the side? Centimeters, centimeters. So for the unit for Z, put centimeters. Guys, how many centimeters are in 1 meter stick? 100. Aha, just like cents in the dollar, right? 100 centi is like 100th or something. Okay. What do you think we're using to measure alpha and beta? Degrees. Aha, degrees. So, well, we'll put DEG for degree. Right. So that when you're writing numbers going down, right, now those numbers are going to automatically have these units embedded. Right. So it's not just like seven what? What is that? Is that 7 centimeters, 7 inches, 7 pounds, 7 degrees? Okay. Now it'll have a unit attached to it. Okay. Going across my table. Let's do this. All right. Do you guys see there are 8 columns left? I should have done this ahead of time, but the next 4 columns, let's put a big box around these 4. Put a big box around these 4 columns. Okay. And then the very last 4 columns, also box those off. So these last 4 columns, I'm going to box these off right here. The box. Okay, and you'll see why here pretty soon. Okay, so you guys see above the columns, I told you to measure some of these and to calculate some of these. Okay? And there are just 2 left I'm going to have you measure. And those 2 are going to be side X, which is in centimeters, and then skip a few columns and over here do side Y, which is also, of course, going to be in centimeters. Okay? Okay. So I got Z in centimeters, I got alpha and beta, or each in degrees, I got X's in centimeters, then skip a few columns, and then your last measured column is Y in centimeters. All right, look at that. All right, so got variable unit. Side X could be a variable. Centimeters could be the unit. Okay. Now, think back to, you might see kind of where this is going, the purpose of this. Okay. Remember I told you guys this is the star poster today? This is the star. Okay. I really want you guys to see this, which is that if you know some information about a triangle or in the future, like vectors and vector component, right, you can figure out everything else about the triangle. So if you know C and theta, you can get B and so on, just like that. Okay. So over here for X, guys, if you know Z and you know alpha, let's start with that, Z and alpha. How can you use Z and alpha to calculate side X? Be what times what?
Is it cosine of alpha times Z?
Oh, yeah. So I'm going to write that in a diagonal here. Go Z times cosine of alpha. Yeah. Okay. Should also tell you side X, and that would be in centimeters, wouldn't it? Because Z is in centimeters, and cosine alpha, that's just a ratio. Okay. How about, here, see if I can prop this up a little bit. A little easier to see. What if you know beta? How can you get X from Z and beta? Sine. Aha. So Z times sine beta. So here. So do Z times sine of beta. Well, you do this. Right. So Z cosine alpha, Z sine beta should both refer to side X. And that's the idea. Okay. Yeah. And there's one more perspective. Did you guys see the dark outline you made around those 4 columns? All refer to side X. It's just different points of view. Like you could directly measure X, or you could calculate it from Z and alpha or Z and beta. Okay? But there's one more way. Here, I'm going to write this down and then see if you guys can figure out where this comes from. So do a giant square root and call this z squared minus y squared. Okay, so that's all underneath that square root. It's z squared minus y squared, all under that radical. Okay. Now, why did I write that? Guys, where does that come from?
Pythagorean.
It is! It is! It's the Pythagorean theorem in disguise. Let's show you guys that's true. Because if you have, here, whip off the right triangle here. If this is x, y, and z, this is a right angle. And you only know the side. Guys, notice this has nothing to do with the measured angles. Although there are measured, there are corresponding angles. Okay? It's just side information. And the fact that it's a right triangle. Okay? I can know that x squared plus y squared is equal to z squared. So if I'm solving for x, so we're doing a timer. Oh yeah, I think we're doing it. Let's do some algebra. Guys, algebra. What's the next algebra step? There you go. Subtract y squared. So x squared, we're trying to solve for x. I'm going to do some process, and the last step says x equals something. Okay? Yeah, subtract y squared over. So z squared minus y squared. Okay. Now what's the next step? Yeah, square root. So is the answer, oh, x equals z minus y. Is that the answer?
No.
No. Why can't I do that? Why is it not z minus y? Yeah, because it doesn't work that way. That's right. Guys, what if this was multiply or divide? Then could I take the square root of these squares?
Yeah.
Yeah, if it was multiply or divide. But if it's add or subtract, you can't do that. It doesn't simplify that way. So I'll just use square root of, and then z squared minus y squared, which is exactly what you wrote in that cell. You guys see that? You see that? All right, let's work on some. Okay. I bet you guys can figure out how to finish off this table. Do you guys think these last three columns all refer to y from a different point of view? So you could go, let's see, take z multiplied by, what if I'm playing off alpha? Guys, z times, what do I do with alpha to get to side y? Yeah.
How do you know it's like what you're supposed to do with each side? How do you like know the sign?
Yeah. How do you know if it's like sine or cosine or what? Right. Now the big point I'm trying to make is that there's multiple ways to get to the answer. So, like these four middle columns all refer to side x from different points of view. They should all tell you the same thing, or pretty close. Right. And these last four columns all refer to side y, but from different points of view. Okay. So the definition of sine and cosine is like opposite over hypotenuse and adjacent over hypotenuse. Right? Well, sine of the angle, cosine of the angle. Okay. But really, what I want you guys to take to heart and to apply is these rearranged forms. So these two little boxes right here. So if you're playing off this angle theta, and you know the side c, which you normally do in this class, right? If you take hypotenuse times sine of the angle, it will always spit out the leg that's opposite of that angle. Notice that side b is not touching angle theta at all, right? But side a is. See how side a is definitely adjacent to that angle, right? So to get that, you need cosine. So then if you take your c, multiply by cosine of the angle, it'll spit out the leg that's adjacent. Okay? Right. Yeah, so get lots of practice with that. Yeah. Right. All right. And that's where we're finished off here. So guys, if I want side y, should I do sine or cosine of alpha? Sine. Yeah, because it's opposite. So I need sine of alpha. Right. What if I was playing on beta? Could I do z times what? It's cosine of beta. So z sine alpha or z cosine beta also each refer to side y. Okay, it's a different way to think of it. Okay. And finally, let's do the reverse Pythagorean theorem. Let's do the square root of. What do you guys think I'm going to write in the square root? Z squared minus x squared. Yeah, and that's all underneath the radical. Z squared minus x squared. But these would all be in centimeters. Centimeters. So when I write down numbers, right, almost all the time, numbers in this class will have units attached to them. And there's only some rare exceptions to that. Okay. Okay. You guys have that? All right. So keep in mind, there are 5 columns marked measure. We've got the 4 over here and then 1 over here marked measure. So we're going to use our measuring tools and measure. Okay. Okay. And then everything else we'll pull out the calculator and see what. Okay. So I'll help you guys out with one of these triangles, and then I'll leave the other 2 to you. So I'll pick my first triangle, triangle A. So a flat guy right here. Okay. and make some measurements. So Z, what is side Z? Oh, guys, make sure you're using, what are you using this class? Centimeters or inches? Centimeters. So use centimeters, not inches, right? Now, mine is, oh, is that's exactly 10 centimeters long. Oh, that was lucky. Okay, so I'll call this 10.0 centimeters. 10.0 centimeters. Now yours is probably different. Okay? So whatever yours is, right, for yours. Okay. Well, I got my ruler out. I'm going to measure the other sides. So I'm going to skip over a few cells to side X. You guys get that? So, well, I got my ruler in my hand. So looks like side X is, this is about 9.4, I think. I'm going to do 9.4 centimeters right there. Skip over a few more cells to side Y so I can get my direct measurement on side Y. And this is it's like 3.4, I think. 3.4 centimeters. All right. So that's my three sides directly measured. All right. You guys ready for protractor? Protractor time? Okay. So I got to measure what is alpha and beta, like how large are those wedges. Okay. Now here's a little hint. If your triangle is too small or your protractor is too big or some combination, could you, if you want to, could you extend the sides? Like, could I put my roller up and just like keep making this longer if I had to? That doesn't change the angle, right? Okay. Right. So if you have to do something like that, that's fine. So I'm going to take the node of the protractor. I'm going to park it right on the corner. I'm going to zero out one of the legs. And then the other leg will sweep through the answer. Oh, wait. It actually sweeps through two numbers. Do you guys see an inside set of numbers and an outside set of numbers? So this sweeps through both the 20 and the 160. Well, for my triangle again. Okay. Guys, what is this angle? Is this 20 degrees or 160 degrees? 20. Yeah, it's 20. So go to alpha, put 20 degrees. Because you guys know in a right triangle, the two angles that we're measuring here would be acute angles. So they have to be less than 90 degrees. Is that true? Okay. So 20 degrees. 160, by the way, refers to this giant obtuse angle over here, which I don't really care about. Okay. How about beta? You guys ready to measure beta? So turn your paper, park this node right on this corner, zero out one leg. Okay. Now I'm going to purposely fudge this a little bit, but you guys will see why I'm in. Right. See, this sweeps through. Okay. Now on mine, this says, well, the inside says 109, the outside says 71. So what is it? Is this 109 or 71? 71 degrees. Okay. So go back over here under beta and put 71 degrees. I always do this. I sort of double mark the unit, but oops. But it makes the angle stand out anyway, I guess, right? 71 degrees. Okay. How you guys doing? You guys doing all right? Okay. Now, at this point, think back to a math class here. I bet you guys know this. In principle, what should the two acute angles of a right triangle always add up to? 90 degrees? Do your angles add up to 90 degrees or pretty close? Yeah, maybe. What about mine? What do these add up to?
Just 90.
91? Okay, so now what do? How many of you guys think I should say, oh, well, I'm just going to kind of erase that and just, I'll just fudge this to 70. Do a little scientific fraud here. How many of you guys think I should do that? Should I do that? Yeah? Or, well, I'm going to say no. I'm going to leave this exactly as my measurement, and I'll tell you guys why. Because different classes have different philosophies. If you were in a math class, then make sure that these two acute angles add up to 90 degrees. Right? But that's not true for a science class. For a science class, make sure that you record only what you directly measure and observe. Right? Here's why. Well, a few reasons, I guess. Right? So whatever measuring equipment you're using, and these are two measuring equipments today, it's understood there's going to be some error in using it. Like nothing is exactly perfect. Okay. So that's understood. There are going to be error bars on the graph. Nothing's going to be exactly true. Okay. Also, whatever you learn to be true, there's this philosophy of science that you should really stick to your observations because sometimes an observation will go against some conventional wisdom, and there might be a reason for that. It might actually unlock some secret of the universe that nobody was even realizing before. Right? I'll show you guys an example. Can you guys think of triangle where it? See, if you also include this right angle, that means all three angles should add up to what? 180. Can you guys think of a triangle whose three angles don't add up to 180 degrees?
The triangle by definition.
Huh? Like a close triangle. Somebody got it earlier. Somebody figured it out.
Is it like
Is it what?
3 dimensions?
3 dimensions! Yeah, yeah. So non-Euclidean geometry. Let me show you guys this. Okay. Guys, that rule about 180 degrees, that only works on a flat surface. That doesn't actually work on a curved surface. Watch this. Here's the Earth. Here's the equator. Here's the North Pole. Here's the South Pole. You guys hear that? Okay. Let's say you're starting on the equator. Ecuador or something. Okay, straight north to the North Pole. You make a 90-degree turn when you're hanging out with the elves. Working on some gifts. Bring them down to some. Go straight back down to the equator. Make another 90-degree turn. Go back where you started. Make another 90-degree turn. Guys, what do those three angles add up to?
270.
270. Ooh, which is more than 180. Okay. So if in real life, if you were like trekking off, like I went, so many miles this way and so many this way and so many this way, it's like my angles don't add up to where it was supposed to. There might be a reason they actually don't. Never mind. All right, little science philosophy there. All right, you guys ready to do these calculations here? Calculation time. So pull up calculator, and all we're going to do is just follow exactly what it says. So first one says z cosine of alpha. So pull up your calculator. Now I know z is, well, for me it's 10 centimeters. So I'm going to type in 10 for 10 centimeters. Okay. Then times cosine. Oh, guys, make sure your calculator is in degrees and not radians. Is your calculator in degrees today and not radians? Make sure it's in degrees. Whoops. So 10 cosine. And then alpha is 20 degrees. Well, or on mine it is. Yours is probably different. That's telling me 9.396926. Can I round that to, what does that round to? 9.4, which was exactly what I measured it. Oh, look at that. It's the same thing. It's the same thing. Next one, z sine beta. Now, one nice feature about these calculators, if you have a big fancy calculation, you're just like tweaking little parts in it. You guys see these scroll keys right here? Scroll keys. Scroll up, scroll over. You just replace what you need to. Instead of cosine, I want a sine. Instead of 20, I want 71 degrees. All right, let's see what is this. 9.46. 9.40, 9.46. Okay, which is pretty close to what I measured, isn't it? Right. Yeah, I'm happy with that. And the last calculation for the side is the reverse Pythagorean theorem. Can you guys do a square root? So hit second root. So now I got a square root key. I need z squared minus y squared. Well, my z is 10, so I'm going to square that. Centimeters, of course. Okay. Then minus, my y is over here. My measured value of y is 3.4 centimeters. So 3.4, square that. All right. Now, guys, when I hit enter, let me make a prediction. Should I get something roughly about 9.4 somewhere there? Centimeters? See if it is. We're going to find out. Moment of truth. Oh, yeah. 9.40425. Yeah, 9.40. Right on the money. Is that working out for you guys too?
Can you show us how to do that?
Yeah, the square root. All right. So the square root. You guys see? Do you have this calculator that I do? Or the square. Okay. So next to the 7 key is, see where it says x squared, but right above that on the board it says square root. So to access that, you have to hit the second key. So you hit second, and then that x squared key to pull up the square root. It should say square root. So you have a square root. Okay. All right. Then I need z squared minus y squared. So I'm going to pop in my measured values.
X.
No, it's it comes from here. So yeah, z squared minus y squared, which really comes from this process here. So I took Pythagorean theorem and just algebraically rearranged it. Yeah. Yeah. Okay, so you okay? Okay. So for z, I put in this value here because that's what I measured for z. So do 10 in my case, and of course square that. Then minus, and then y squared. well, here's my measured value of y. So I'll pop that in and then square that. Okay. Yeah, that's where I got that number from. Here, I'll do these last 3 calculations with you guys too. Okay. So this one says z sine alpha. Now, if you refer to your picture, if you start with z and you multiply by sine of alpha, that gives you what side? Y. Right. Now I have a measured value y, 3.4 centimeters. So this better come out to pretty close to 3.4 centimeters. Let's see if it does. Take my 10 centimeters, multiply by sine of 20 degrees. Oh yeah, 3.42 centimeters. By the way, do I really know that 2 is a 2? Probably not. That's too much precision. Probably talk about that upcoming next few days. Okay. But on the AP exam, AP graders are not sticklers about sig figs at all. So if you always do 3 sig figs or something, then that's fine. They'll take it, even if you don't technically be able to know it. Z cosine beta. I know in chemistry they were sticklers about sig figs, but physics not so much. Z cosine beta. Z cosine. My beta was 71 degrees. Let's give me 3.26. Okay, so it's off a little bit more, but it's pretty close anyway. So that's good. And then reverse Pythagorean theorem. Square root of z squared minus x squared 3.41. Ah, it's also right in there. Okay. So you guys see how your measured value for each side? You can get there by sine or cosine. It should be almost exactly the same thing, ideally exactly the same thing. But there's also a Pythagorean theorem way to get it too. Okay, you guys can do those? Okay, so yeah, all right, so that class flew by. I need to give you guys some time in class to also do these other triangles and these 10 triangles on the back. So I'll work in some class time over the next couple days, but yeah, one day at a time. All right, let's wrap on today. All right, you guys have a good night.